Sponsors, they're up there. Thank you, sponsors. And I'd like to thank again Erica and the staff of the Saban Research Institute for supporting this and making sure the food's on time and it got cleaned up after the party last night. And I think we're ready to start. But you're going to have the pleasure of Dave Cale doing the introductions today. It's his birthday today, so we wanted to give him a special job and embarrass him in front of the whole crowd. So David's doing the MC for the morning session. Take over.
So I think you guys are in for a real treat this morning. We have three really excellent speakers talking about a vast array of different sort of techniques from machine learning and data mining, representing various different approaches. I'm only sorry that Stuart Russell couldn't stay with us today because we're also going to do a panel and we wanted to watch all these speakers go at it and argue their different approaches. So first up, we have Professor of Computer Science from UC Riverside, Christian Shelton, and Stuart actually gave him a better introduction than I possibly could yesterday when he said that Christian was going to try to convince all of us that Stuart was wrong. So anyway, without further ado, Professor Shelton.
Thank you. I think I can manage this. Thanks. I don't know if I'm exactly going to try to refute what Stuart said, but I'll maybe try to build on it. I have a little bit different take. So I do work in many areas, and one of them is in continuous time models. So what I'd like to talk about a little bit is our continuous time models, what the advantages are, and then a little bit of applications, the results that are 2 days old of that in a patient ventilation system. So I guess yesterday it was mentioned that patients are data. I guess I take a slightly different view of that. Patients are dynamic systems of which we gather data from. And I think that was understood by the statement anyway. And those systems evolve in continuous time, or they don't naturally have a time clock. At this moment, variables can change, and then they hold constant. At this moment, they can change. And the measurements themselves, of course, might be discrete in time and such, but they're taken asynchronously, and they just the fact that they're discrete in time doesn't mean the system itself is. And I think it's important to perhaps model the system in continuous time, even if our events or readings are discrete. So why would we want to do that? Well, you might want to classify the systems. Is it more like this? Is it more like that? You might use the model for control theory. We've done a little bit of work on that. How to cluster different things, or maybe just to explore the data in general. You'll see the models we have some qualitative explanation capabilities. So let me talk a little bit why I don't think time slicing is always the right answer. So if your problem has a natural time clock, then obviously you should be modeling it as a discrete time thing. So maybe you're trying to model the traffic delays in the morning in general, right? Say in the LA area. I hear there are traffic delays in the LA area. So then each morning is sort of like a separate event, and you talk about this morning and then the next morning and then the next morning, and that clearly has a time clock. But lots of processes don't have such a natural time clock to them. So you have to pick, if you want to do discrete time, you have to pick some delta t at which to sample the process. So an interesting thing is the estimated structure, so that is if you're trying to estimate independencies in your model in order to build these sort of graphs, these circles and edges that Stuart was talking about last time. The estimated model structure is unstable with respect to the delta t. If you have a choice over delta t, then both theoretically and empirically we've demonstrated that the model structure is unstable. So let me give an empirical example, very simple. So in this example, we took a chain of 4 variables, top, middle, lower, and then lowest. And the top variable just changes as it wishes, according to some process, and each variable tries to follow the one above it. Okay, and this is a continuous time process, and then what we did is we sampled that process at different rates and for different amounts of data. So, this looks like this will work. Yes. So different rates, and then, so this is a slow rate, and this is a quick rate, and then different amounts of data, and then we tried to estimate the corresponding dynamic Bayesian network. okay, which is that, right, okay, so you get messes over here. Here you're actually estimating the stationary distribution if you have enough data because it's too big. The natural time rate's about 1 on this process. Okay, so one thing to notice is, yeah, if you have a lot of data and you have very fine time granularity, this is pretty good. But otherwise you get structures like this. And, depending on what your data, you get slightly different structures, but these are indicative. The other thing is, here's my data size again. And now I'm going to ask, okay, I built that model. How well does it predict future data? Okay, here's the true model, if I knew what it is, how well it predicts future data. You want to be up here. And you'll notice that depending on the amount of data you have, a different time slice width will perform better. Okay, so it's not just to say that for this particular process, I need to pick this amount of data. It's for this particular process and this amount of data that I have to build my model, I need to use this time slice width, which is that's highly sensitive, right? I don't want to do that. And just by comparison, the model I'm talking about looks like this. Now, of course, this data was drawn exactly from the model I'm talking about, so that's not entirely fair, but okay. All right, so there are also theoretic reasons you don't want to do this, and I don't know if I want to get into all those because apparently I don't have all morning. I don't know, but okay. So, but you essentially are trying to play off two things. If your time slice is too large, you miss detail, right? In that extreme example, I'm just estimating the stationary distribution. I don't get any of the dynamics. If it's too small and you had enough data, you say, well, that's fine. But now it's very computationally intractable because in order to go 1 second, I've got to, integrate across 100 time steps or whatever that I thought was necessary just to capture all the little fine detail. So we might say, well, what I'll do is I'll just try to be clever about my computation here, and I'll let delta t go to 0 and see what I get. Well, then you get a continuous time model in which you're clever about how to compute in it, and that's what I'm going to talk about. Okay. So. The other thing is interesting. If you believe you have a Markovian system, that is, you believe the variables you have represent everything there is to know about how the process will evolve in the future, and you have a continuous time model, you can time slice that model at a particular delta t and end up with a discrete time Markov process. Okay. Well, there should be a not equals here. But the reverse is not true. I can give you a system that over this particular delta t, okay, is Markovian, and there is no continuous time Markovian process at which if I sampled at that rate, I would get that process, okay? Think of a process that switches exactly every time step. There's no continuous process that's going to get me that because halfway in between where I know this is not a Markovian process, okay? So, and the other thing is that basically if you have different time scales involved in the same process, some things are evolving at microsecond rates and some things are evolving at second rates and some things are evolving over the course of days, that at least in the continuous time version of this is a direct problem that hits you right up front and you have to solve immediately as opposed to hiding behind the time slices. And you get algorithms that I think more directly address that and are more efficient. Okay. So let me describe a little bit what a continuous time process looks like since it's not something people typically run across. So I'm talking about a discrete process here. That is, the value of the process is discrete. It evolves in continuous time. And later I'll touch on what happens if the value is continuous. So I'm basically describing a distribution. Process is another word for a random variable over a sequence of time. I'm describing a distribution, and a sample from that distribution looks like this. At some time, it was in the blue state, and then at some time, this is a real value time, so it actually has an infinite number of digits of precision. At some time, it switches to the green state, and then it sometimes switches to the red, and sometimes switches to the blue. And you can imagine all possible sets of trajectories that look like this, and I'm going to describe a distribution over those. Okay. And I'm going to make the assumption that it's Markovian, and I'll show a little bit why that's not so draconian. And that is that if I know it's in the green state here, it doesn't matter anything else what happened in the past. The fact that it's green here is all that really matters to predict how it's going to go in the future. Okay. So these processes, just to give a little bit of math and numbers, these processes are described by sort of two sets of parameters. One is what we call the Ware distribution. This is basically a stochastic matrix that says if you're in state, 1, then 2/3 of the chance you'll move to state 2 next, and 1/3 of the chance you'll move to state 3 next. Okay? And there's nothing on the diagonal because if I don't tell you anything, then you're staying in the same state. Right? There's a continuity to time. And then, that's what I just said. And then there's also a when distribution, which is, okay, if I'm in this state, how quickly till I leave? Right? And for those of you on this side, I can do this. So here, see 3. Okay, so, and this is basically a rate. You think it was like 1 over the half-life. Okay, so it's an exponential distribution. Why is it exponential? Because that's the only memory list distribution. In other words, the fact that I've been in this state for this long can't tell me anything else about where I'll go. So it has to be exponential if you're Markovian. Okay, and then the more typical thing is I take this and I expand it out and I multiply them together and I get up this, a rate matrix, which is essentially these things here scaled by the corresponding rate. And the fact these come out to integers is because I constructed it by hand. Right, so this says there's a rate 3, and 2 over 3 of the time it goes here after leaving, and 1 over 3 of the time it goes there after leaving that state. Okay, so the rows sum to 0. So, so you might say, okay, how is this related? Can I make an understanding of it? The easiest way to sort of understand this rate matrix is if I want to know the conditional distribution, given I'm at some state at time s, and at what state I'll be at time t, that's a matrix for every possible value of xs and every possible value of xt, matrix. That is equal to the exponential of this rate matrix q times the delta t, where that is the matrix exponential. So here's the Taylor expansion, or you can take an eigenvalue decomposition and exponentiate the eigenvalues. You do not exponentiate each element individually. Okay, so basically that's a way you would either get a discrete time process out of it or sort of understand. And the real take-home point is that the core thing you need to do is calculate a matrix exponential to, or similar things, to work with these models. You might say, that sounds really complicated compared to what you have to do with a DBN. And the answer is no, actually, this is what you do have to do in a DBN. It's just you do it as you unroll the thing. So in a DBN, you're talking about different time slices, and you unroll them, and it gets more and more coupled and complicated as it goes together. And all you're doing is you're seeing this effect that's sort of masked by the structure of this static time. Okay. So the reason that there are discrete time models that don't correspond to continuous time models is the fact that while the matrix exponential exists, the matrix log does not. So that's just something curious. Okay, so that was all fine. That describes a 3-state system, not very interesting. So if you want to do something more interesting, you need a system that has values of variables and a large state space. So we defined a continuous time Bayesian network, which is essentially the equivalent of a dynamic Bayesian network, but for continuous time. So it's a graphical model. So I'm going to have nodes. Each node represents a process, some particular variable of interest inside of your system. And edges represent instantaneous influence, or essentially causality in this model. So here's the simplest such thing I can draw. A is a variable. B is a variable. A's evolution over time doesn't depend on anything else. It just goes off and does what it wants. And B's evolution over time depends on A. Okay? So this means that I'm going to describe a rate matrix for A. I'll just pick this one out of a hat. Okay, so here's a rate matrix that describes how the process, right? It doesn't depend on anything else. It's just how it goes off. It's a simple binary process. And now B needs 2 rate matrices. That is, at time instance, when A is equal to 0, then it'll evolve according to this rate matrix, and when A equals 1, it'll evolve according to this rate matrix. Okay, so B is also a binary variable, and I have this. Okay, so I can do this now. Provided there are only a few parents to every variable. Each variable only has a few number of parameters, and therefore this scales polynomially with the number of variables, and it's exponentially. And then if you want to think about combining this whole thing into a single system, what are the semantics? Well, there is some single system, the A-B system, which has 4 states, A0, B0, A1, B0, A0, B1, and A1, B1. And there is an equivalent Markov process over the whole thing. Essentially, no 2 variables can change at exactly the same time. Those correspond to exactly the same changes. And then I can just copy the corresponding rates over. So in the interest of time, I'll just say that works. And you get something like this. So if you have a set of these rate matrices for each variable conditioned on its parents, you don't want to, you can combine them into a huge rate matrix here. But this rate matrix here that describes the whole process is exponentially large in the number of variables because it has one row or column for every possible assignment to all the variables, right? So if you have n binary variables, there are 2 to the n possible assignments to those n binary variables. All right. So just a quick example. So A is a process that evolves all by itself. So if I start the system off with A is 1 and B is 0, then, and I look over time of what, if I covered my eyes and then opened my eyes at that time, what's the distribution I would expect to find the system A in, then it follows an exponential, it's basically converging to a stationary distribution. Okay. But now if I do the same thing for B, I don't end up with an exponential. And that's because, while A is a Markov process, B, if you marginalize to B, is not a Markov process. This is like a hidden Markov model. Okay, the underlying state sequence is Markovian, but the observations are not Markovian. This is exactly a hidden Markov model in a CTBN framework. So you can get interesting dynamics by hiding one variable and only looking at the others. So that's why I'm not too worried about having Markovian dynamics. I'll just add hidden variables to explain. All right. So last thing I'd like to talk about is, so what does it look like to have evidence or data in such a model? So here's a simple CTBN. Cycles are fine, by the way. That doesn't bother us. So here's a simple CTBN. So, for each variable, I'll have some observations. So maybe the eating variable I observed completely. And basically what that means is that starting at this time, I observed that he was eating and then not eating and then was eating and then not eating, like this. But that's not the only kind of evidence pattern you can have. You can have variables that are completely hidden. I don't observe anything about them. Or you can have variables like this. So maybe, I observe hungry, and at this point of time I lost my data, so I don't observe anything there. Or maybe I have an observation like this. This is supposed to be infinitesimally small, so I have a point evidence at this exact instant. I knew the value and not before or after. I can even have other sorts of things. I have evidence that a transition happened. I just don't know what kind of transition it was, or other sorts of things like that. Those are all possible. So the range of possible evidence or data you might have is larger. Okay, and then you can answer questions like, what's the chance, given all that information, that he was hungry here? What's the chance his stomach was empty over that interval? What's the total expected amount of time the stomach was full? Statistics of the trajectories that I didn't observe. Okay, so the next question is, what can you do with that? And the answer is, if you have something if you know something about dynamic Bayesian networks and you have an algorithm there, we have the equivalent here. So you can't do exact inference, and you can't do exact inference in a dynamic Bayesian network either. And then these are like standard statistic methods for approximating inference, and you can see that somebody over the past 5 or 10 years or so has produced the equivalent for continuous time Bayesian networks. Okay. And then the other thing you might want to do is that's like I have a model and I want to try to estimate those questions. The other thing you might want to do is I have some data I'd like to try to build the model. So if you have complete data, every variable you observe everything, that's trivial. If you have incomplete data, then you use something from I mentioned before, along with the expectation maximization algorithm. And the other thing that's interesting is you might want to learn the structure, not just the parameters, but I want to learn what are those edges, what are those arcs. And one nice thing about a CTBN is that the structure learning problem is much, much easier than in a dynamic Bayesian network. In a dynamic Bayesian network, you have, at least for the intra-time slice arcs, you have an acyclicity constraint, which makes the search problem very hard. I have no such constraint here. So structure search is polynomial instead of, and you get the optimal answer. And that means that doing what used to be incredibly difficult structural EM algorithm in this, because the structure learning step was approximate and so it caused problems, is very tractable in a CTBN. Okay. So typically at some point in the talk or after the talk, I get the question, well, that was all great, but I have a continuous variable, right? I have temperature, I have position, I have blood pressure. And so the answer is, okay, so if you want a general continuous time, continuous state Markov process, the answer is alluded to by Stuart yesterday is a stochastic differential equation, which sounds ugly and kind of is. If you want the simple case, what's the simple case of that? So the equivalent of a Kalman filter, or the equivalent of a linear Gaussian model. Basically, you can build that from Brownian motion. You end up with this particular stochastic differential equation, which can be solved. And as an example, if I knew this state at time 0 and I want the distribution over at time t, you get a normal distribution with this formula for the mean and this for the covariance. Okay, and they look ugly, but they have matrix exponential again, and this thing's kind of related to the matrix exponential, so they're things we know how to calculate from before. And essentially, if you want to do the stuff from before, filtering, smoothing, tracking, that is, I have a model and I want to try to figure out what's going on based on some data, that's easy. If you know the Kalman-Busti filter, this is sort of like a variant of it. The hard thing is if you have data that's not evenly spaced observations, that learning or estimating a process from this is very difficult. And the best literature actually in this case is the economics literature. They use similar models to price options and do other things like this, okay? And they have interesting data there, and they have some estimation methods, but that's a little difficult. So for this talk, I'm going to take, somewhat ironically, I have a continuous time, continuous state system, and I'm going to argue that we should discretize the state and not the time, or at least I'm going to try that here. But clearly moving in this direction is important. So with a few minutes, I'll try to get to the results. So we've applied this to many things. We've applied it to social network inference. We've applied it to computer network intrusion detection. We've applied it to a lot of things. So in the past month, we've applied it to ventilation monitoring. So that is, we want to have a model of how a patient responds to ventilation and ventilation settings. Okay? This is joint work with a number of people who you may or may not know here at CHLA, and then my graduate student at UCR. So why do you want to do that? Well, there are some quantities in this model that are invasive or difficult to test. Okay? And what I'd like to do is build something that will monitor those things and tell me either when you need to test them because then my error bounds are large, I'm not sure what it is, or maybe I want to use them to take control actions, like ventilator settings. So the data, well, it's no longer approximate. This was when I had the slide, I wasn't sure. It's exactly 103 patients, sorry, who are intubated and on a ventilator. And we picked these ones because we have full data on these variables. So this is like the initial study. And our goals are really to estimate the blood pH, the thing you're trying to control with the ventilator. But as sort of a surrogate or a reasonable first step, you might try to estimate the partial pressure of CO2. Okay? And both of these things would be invasive to test. I mean, you can test them. We have tested these patients. They did have them tested, but in general, you prefer not to. Okay, so we have a series of variables here that are the non-invasive measures, the end tidal CO2, which is measured at the breathing tube, some settings of the ventilator, some composite indexes. These three are all sort of composite indexes of various forms. And then some invasive measures, so pH and partial pressure of CO2 I mentioned. Here's partial pressure of oxygen and some other things that we may or may not have data for. So you can throw those all in. And, well, okay, so first, here's a rough outline of like how you'd expect the system. Well, we're not modeling the kidneys here, but other than that, so you have lung injury, which is giving you these scores, and the lung and the heart together dictate sort of what blood flow you have to the lungs, and then here's a box that's sort of modeling the CO2 removal that's related to your pH and affected by ventilator settings. Okay. So if you throw those all in and you ask it to learn the structure, you get something like this, where the top variables are non-invasive and the bottom variables are invasive. And I'll say this is just sort of a preliminary result. I don't want anyone to go make medical decisions based on this. Please don't do that yet. I mean, we want to get to that point at some point, but not right now. So here you can see that the partial pressure of CO2 is related to the end tidal CO2. It affects it. That makes sense. And the pH is affected by the lung score directly. This is kind of interesting. It's standing in as a surrogate. I'll discuss that in a bit. But if we just limit ourselves to this box here, we can build a model like this. A few things are interesting here. Let's see. So these two are very heavily related, and so they depend on each other. The lung score here is standing in for some other things about the body because we don't have any hidden variables at this point, so that's affecting this. It's not an unreasonable model. It's not clear exactly if it's right yet. As I said, we've had this for 2 days, so I don't know. But just to give you an idea of what you would would also get out quantitative information like, let's look at the partial pressure of CO2. It's affected by these two variables. So each of these variables in this case has been discretized to 4 values. So there's 16 possible values for these. Here are 3 of those sets. So if SF is between 172 and 235 and OSI is between 1.5 and 5.8, then I end up with a rate matrix like this to describe how the partial pressure of CO2 will move. So the rate at which it leaves the 50 to 62 range and then evenly jumps to one of these two here. As an example, you get fairly different dynamics for this variable depending on what those two variables are. Okay, again, don't make a medical decision based on this yet. Okay, so but I do want to say, okay, so what can I say about having done this little study? The first is we've had the data for about 4 weeks, and we ran the results this week. So I don't want to say too much, but one is that our goal here is sort of to model causality inside the patient system, but we're modeling some other things too. we're modeling the causality of the entire system that includes the doctors and the ventilator and how the ventilator reacts and all the rest of those sorts of things. And that's probably okay, but I'd like to be able to determine which things are happening inside the body I don't have control over, and which of these effects are, through the outside and I can actually control. So in some sense, if you record the interventions, I think that helps eliminate this. If I have variables that stand for those interventions, then I will learn that the intervention is what was standing between this variable and that variable. They don't directly go through. It's this variable was causing this intervention, and the intervention was causing this change, as opposed to this variable was causing that change. And that makes a large difference in terms of understanding the system. And then there are obviously some things we want to do. We want to add some hidden variables. There are clearly hidden variables there. And we can do that. We just didn't do it yesterday. And then we're doing some value discretization effects clearly here, and we want to study that more carefully. Okay. So what are my final notes? I think patients are continuous time systems. I don't think anyone's going to disagree with that. The only question is it useful to model them that way? They have there are things going on in the human body that have vastly differing rates of change. And the measurements are, vastly different rates and sporadic and all sorts of other things. And I think there's no reason with modern computer technology you shouldn't have a model that at least admits that. I mean, at the end of the day, you're going to be doing your computations on a CPU that takes steps. Sure. But that doesn't mean that the thing you're reasoning about or you're trying to compute has to have the same time slicing. One nice thing about the medical data we have is that it's time-stamped. There are lots of data sets out there in lots of different areas that no one bothered to record accurate time steps for, and therefore you have real hard time discerning causality, actually, other things like this. So I would encourage anyone who's designing systems to take accurate time measurements. They can be very useful. And one trick there is in synchronizing various systems. Yeah. Or at least understanding what the error might be, because we actually can model error. If we know that this it gets more difficult, we can model error. But having some accurate notion of time, I think, is very helpful. The final thing is all this was implemented in a code base that's freely available. We've had it up for a couple years. We're about to release a new version of it. It's available here under the GPL. And this code base not only implements everything we've done, it implements almost every other algorithm that's been developed for continuous time Bayesian networks, and they've been tested. There are a couple that haven't, but almost all of them are in there. We're attempting to add everything in there. So if you have an interest in it, you don't have to go implement these algorithms from scratch. Thank you.